So Tuesday, we went through and looked at some names for some of the common groups. So we listed all those off, and we added a couple more to this list. It would have been nice if I typed those in. Anybody remember the more that we added? Noble gases are actually already there. Yeah. Group 3 to 12 are known as your transition metals. Ow. And then elements, what is it, 57 to 71 and 89 to 103. 57 to 71 known as the lanthanides. Sure, why not? Let's call it lanthanides like that. 89 to 103. We got our actinides. Those are named just based on that first element in the sequence, so 57 or 89. Together, whoops. As a group, those are referred to as our inner transition elements or transition metals. State. Okay? So you've got some big ones that are kind of important that show up. I do expect you to know noble gases for the test. Whoops, noble gases and halogens. Chalcogens and pnictogens, don't expect you to be able to predict or reference which ones those are. The alkali metals and alkaline earth, I also don't really expect, though I'm probably going to get in trouble for saying that and recording it, because most people do expect you to kind of know, oh, we're referring to the alkali metals. That's anything under lithium. Okay? So you might be expected to know those in future classes. I just won't expect you to know those here. I do also expect you to recognize transition metals, because we're referring to a huge section of the periodic table with those. So I do expect you to be able to identify that. Likewise, the name for your inner transition metals as well. Okay? As far as the chemistry that we're going to evaluate, we're not going to look at the chemistry of our inner transition metals as far as I know this semester. The transition metals we might see a little bit of information on, but that's kind of questionable as well. Okay? We then looked at some periodic trends, and one of them that we looked at was the atomic radius. Right? And as we look within a column, we could predict the atomic radius fairly well. Okay? What happens as we move from, say, hydrogen down to francium? It's the difference between hydrogen and francium. There's lots of differences, but come up with one. We could look at size already, okay? But why is the size different? So now we can go back to another reason behind it. What's that? So we could start to look at the mass. What contributes to mass? Protons and the neutrons. When we look at where the protons and neutrons are located, that's where? In the nucleus. If we now compare our nucleus to the size of an individual atom, is the nucleus really all that important? No. Remember, the nucleus was super, super small. If we made it a marble, the atom was the superdome. Okay, so just by increasing the number of protons and neutrons, going from hydrogen to, say, francium, that doesn't really seem to do much to the size. We might expect it to increase, but the nucleus isn't really contributing to the overall size. What else is increasing as we move from hydrogen to francium? The number of electrons. Okay, we haven't discussed yet, but we will get into that today, where the electrons exist. And those are really what's contributing to the size effect. So when we go from hydrogen to francium, we're adding in a ton of extra electrons, and by a ton, apparently a ton equals 87 electrons, and that makes it a lot bigger. Okay, so when we look through a column, it seems to make sense. Our radius would be proportional according to what they're looking at. If we go down our column, we expect our radius to get bigger because we're putting more things into it. Okay? We could look at it as the textbook's got it referenced, and it could be decreasing as it goes up an individual column. They're both saying the same thing, it's just different perspectives. Yes, that's it.
Does it increase as we go from
You increase as you go from hydrogen to francium. If we go up a group, we're going from francium to hydrogen. Yeah, I know. I don't know why they're looking at the up. That seems confusing to me too. Okay. Questions about that first one? Okay. To me, that first rule kind of makes sense. Okay. The second one is a lot trickier. Because as we move across a column, goes from, say, hydrogen to helium, or lithium to neon, we're also increasing the number of electrons and protons, which we would then presume what would happen to the atomic radius. We would expect it to increase as we move from left to right across the periodic table. Okay? What's our actual rule? Decreases. Okay? The explanation for why it decreases has to do with where the electrons exist. Okay? So at this point, we can just start to get these rules beaten into our head and try and remember them. So we go down a column, what happens to the size? Increases as we go from right to left. Increases as we move right to left. Left to right was decreasing. Okay? I switched it on you just to be a jerk. Okay. So this is correct. As we go from left to right, what happens? It decreases. Okay, it's counterintuitive. We would expect as we add more electrons, we would expect it to get bigger. That's wrong. It does not happen in this case when we move across a column. And there's a very good reason for it, and we'll discuss that later today. No. Density is the relationship between mass and volume. Do electrons contribute mass? It's insignificant, so it doesn't go back to density. Yeah?
So if you remove from hydrogen and compare it to mercury, since you're going down, should be decreasing, moving to the right, which is decreasing? What would you say about that?
So when you move down a column, you see substantial changes in the size. Okay? It's really big differences. When you move across a row, when you move into future classes, in particular organic chemistry, what I end up telling people is within a row, we see no size change. Okay? So the left to right size change is there, but it's minimal. Okay? So it's a small difference. So if we're going to compare hydrogen to mercury, we're looking at opposite directions. As we look left to right, we would expect it to decrease because we're looking at mercury being to the right of hydrogen. But mercury is lower than hydrogen, so we would expect it to increase. Which effect plays a larger role? Up, down, left, right. Up, down. Yes. Left to right is not energy levels. Up, down is energy levels. Yeah, and we'll talk about that. Okay? So we could look at images. So they went through and tried to scale images. So you see as you move from top to bottom, we see fairly large differences, okay, in the size of our atomic radii. When we look across the column, or sorry, that's not across the column, across an individual row, you'll notice that we don't get as big of a difference. Okay, particularly when we move over here, boron, carbon, nitrogen, oxygen, fluorine. Yes, the size gets smaller, but it's not that much of a size difference. Okay? So within a column, we see massive size differences, okay, as we move down the periodic table. So we move left to right, the size difference is there, it's just not as drastic. Okay? Questions about that? Okay. So what we could start to do is start to put trends on our periodic table. Okay? So this could be something that if you don't want to have to memorize these trends, you could go through and as soon as you get your exam, draw a little box representing your periodic table, maybe write francium, or in this case rubidium, and helium in the upper left-hand corner, and rubidium in the lower left. Sorry, rubidium lower left, helium is in the upper right corner. And you could draw on these arrows representing those size changes. So as we move up a column, this whole decrease up-down thing is confusing the crap out of me. Okay. So come up with whatever arrow system works best for you. I personally don't like their arrow system, but okay, that's what the textbook's showing you. Okay. So make sure you come up with some way to represent that as far as how you want to draw those size differences. The other big thing we could look at is metallic character. Your lower left-hand corner is the most metallic. Your upper right-hand corner is the least metallic. Okay? Is that believable according to where our transition is between metals and nonmetals? Yeah. If we take a look at that diagonal line, the lower we are, the more likely we are a metal. The higher we are, the more likely we're a nonmetal. Left to right across our diagonal line for our semi-metal transition, same deal. Okay, so lower left-hand corner is the most metallic. Upper right-hand corner is the least metallic. Okay. That will play a huge role as far as understanding different principles later on when we look at bonding. Okay, so you do want to remember that metallic rule. We're going to change it a little bit as well. So this one's a bit odd because it's diagonal. But when you look at a periodic table, how often are they diagonal? Or not. So upper right on your periodic table would be helium. So upper right. And we have our lower left. Hey, hello. Being our rubidium. Okay? Questions about that? Okay. Remember, these are general trends. They aren't exactly perfect. And if you go through, you can find exceptions to these general trends. Okay. For the most part, they hold fairly true for what we're going to be working with, which is primarily the upper half of the periodic table, 1 through 36. Okay, that's less than half, I know, but 1 through 36 is primarily what we'll work with. Okay, questions about that? Predicting physical properties. Okay, so this is what we were saying Mendeleev was able to do. So can we predict something about francium? So where is francium on the periodic table? Lower left, underneath cesium. Okay, so first off, what will we say about its metallic versus non-metallic properties? It's probably metallic. Atomic radius. Okay, how could we predict its atomic radius? What would we want to do? Okay, should be really big. It should be bigger than all of the other elements before it. Okay, so its atomic radius in nanometers should be bigger than 0.266. How much bigger?
So it's between rubidium and CS.
Where's francium? It's not between cesium and rubidium. It's lower than on the periodic table. Okay, so if we were going to put in a column or an extra row here at the bottom, we could put in francium. What would we predict for our atomic radius? It should be bigger than 0.266 because it's lower than cesium. How much bigger should we do it? Why are you saying 0.2 or 0.02? Take a look at the difference between these as we move through. Okay? We're comparing that difference as we move down the column and approximating how much of a difference that is. What is that difference? 0.03-ish, right?
Yeah.
Next one?
5, 4, 2, 1.
It's not 2-1. It's got to be closer to 4, isn't it?
Yeah.
Okay, 0.02, 0. Actually, that actually is starting to get pretty close to 1.
Yeah.
Okay, so we can put down the 2. So it was a good approximation. What might we guess for our francium?
0.27.
0. That's getting way too many numbers on it. We can drop in 2.8286. Okay, get the idea with the approximations. So what we're doing is noticing that trend and guessing at how much it's adjusting. And when we look at the elements above it, how much does it change as we move down one tick within our column? How about the density? What happens to the density? Also increases. So what should we predict for the density of francium? something bigger than 1.87. We could go through and again compare the differences between each of these to come up with some approximation. What are we, 0.5? Oh, that's interesting. That actually went down by what, 0.1? That one went up by 0.7. That one went up by 0.3. So the density doesn't give us as clean of a transition, but we do see in general that it is increasing. So we might predict for a density maybe about 2. Okay? Get the idea on what's happening with these predictions? Okay, this is one of the big things that Mendeleev was able to do. The organization of the physical properties that he had available to him, he could then use and predict those new properties. Okay, let's take a look at melting point. What happens to the melting point? So I saw some heads shaking. No. In general, what happens to the melting point as we go down a column? It drops. So it goes down. How much does it go down? Okay, seems to go by a lot at first and then slowly get less and less. So what we would do, a number that would be reasonable, first off, would have to be less than 28. Okay, why less than 28? If it's greater than 28, we're going up the column, not down our column. Okay, how much less? Okay, well, we would go back to our melting points and see if we could come up with a pattern. The difference down here is what? Almost 80. Difference down here is... Okay, apparently you guys can do math better than me. Difference down there, 20-ish. Difference down here, 10. So should I decrease by, say, 100 degrees? No, why not 100 degrees lower?
Half of the previous difference.
Because if we look at our differences, it's slowly decreasing all the way down, but it's that number it's decreasing is also shrinking. So our guess might be 5 degrees lower, say 23.4 degrees Celsius. Okay? Do I have everybody on the same page on this now? Okay, just wanted to make sure.
What's the assumption for the temperature when you say the natural state on there at 28 C?
Temperature, I believe, let's see, does it actually say? I'm going to take a stab at it and say it's standard pressure at 1 atmosphere, and then room temperature would be my guess, which would be 22 degrees Celsius. And I don't see that assumption on there. What was your question? Sorry, after that? Nothing?
I was just saying, whatever that floor is, it could drop below that and you just put on there.
True. Oh, that's an interesting point. Yeah. More information I want to bring into it, but yes, you could add that information to it as well. Okay. So that helps us predict some of the physical properties that we could go through and observe. So they've got lists. Whoops, there it goes. Okay, we could also go through and predict something about the chemical properties. So how does it react with other elements? The most common element that they used to react with things was oxygen. Oxygen ends up being one of the most reactive elements that we have on Earth as far as we're concerned. It tends to react with pretty much everything. Almost everything is in some oxide state. Okay, look at water. What is water? It's the oxide of hydrogen. Okay, what is rust? The oxide of iron. Okay, oxide or oxygen tends to be very, very reactive, and so it will react fairly quickly with most species and generate their oxide states. Okay, that oxide state is dependent upon how that individual element wants to react with oxygen. Sometimes it'll react where it only picks up 1 oxygen. Sometimes it'll react where it picks up 2, okay, or 3. So it depends on the different reactivities of that individual element. It turns out within that column, we see very similar trends. Within an individual column, if the first one reacts with only 1 oxygen, the next element in that trend also only going to react with one oxygen. Okay, so as an example, if we take a look at lithium oxide, okay, when we form an oxide of lithium, it's required to have 2 lithium atoms per single oxygen. If we go to sodium, okay, sodium is immediately underneath lithium. And what we said is within an individual column, the chemistry tracks. We get the same chemical types of reactions. So if we didn't know what the chemical formula was going to be for sodium oxide, but we knew lithium oxide, we could say, more than likely, it's going to be 2 sodium ions per oxygen. And sure enough, that's what we end up seeing. Okay? So let's take a look at another option. If we've got the formula, oh man, so much for covering up answers. Here, quickly, close your eyes. Formula for the chloride of calcium is calcium chloride. What's going to be the formula for the chloride of barium? So what we would do is look up where calcium is. It's in column number 2, or group 2. 1, 2, 3, 4th row down. We're looking at calcium with the atomic number of 20. Where is barium? 2 underneath it. So they're in the same chemical family, or the same group, which means we would predict the same chemical responses. So if I was going to react barium with chloride, I would probably predict that I would get BaCl2, matching the same formula as the calcium, except instead we use barium instead of calcium. Okay, so new question then. Okay, because you already had that answer. So let's make one where you don't have the answer. What is the formula for the bromide of calcium? So this question is actually going to ask a couple different things. Some of this we haven't officially talked about. What element is bromide? Are any of the elements up there named bromide? Br is named what? Bromine. Okay. Why are we calling it bromide? We've changed its chemical state. Okay, so it's no longer bromine, it's bromide. We'll talk about why that name changes, because it's not officially bromine, it's technically a new species or a new chemical, Br minus. So it's still the same element, just with a different reactivity. So we're looking at Br and Ca for calcium. Okay. Well, the information that we're given is about calcium chloride. So we're looking at still calcium in both cases, so that's not anything particularly special or interesting. So for our formula, we could write out our Ca. We want for calcium bromide, so we go back and compare our formula. Our formula gives us chloride. Where's chlorine versus bromine? They're in the same column, right? So what would we predict for the reactivity of bromine in comparison to chlorine? Should be the same. So when I reacted chlorine with calcium, I got calcium chloride, CaCl2. When I react bromine with calcium, what would I expect? Calcium bromide, CaBr2. Okay? Makes sense? So we can predict on both sides of it. It doesn't have to be just the first element in our formula. Yes? Run that by me again, how I got calcium bromide. So the question that I asked is, what is the formula for the bromide of calcium? So what this question assumes is some nomenclature stuff that we haven't looked at. Our formula is going to try and condense the name, our bromide of calcium, into a formula system. What symbol do we use for calcium? Ca. What symbol do we use for bromide? Br. What we're going to do is then put those next to each other. But remember, every compound or every atom can react slightly differently. We can generate different possible products out of this. So this could be Ca4 and Br1. Those numbers could be different. Okay, so when we first come up with this question, we don't know those numbers. Those would be X and Y.
How do you know which way to put them?
The organization on that we haven't talked about yet, but we can reference that quickly. When you go through and put together an individual formula, you put your most metallic first, followed by your non-metallic. So that's why we pick up calcium bromide. We do CABR. Okay. As far as the test would go at this point, since you don't know that, it's multiple choice, you wouldn't have to figure out the organization. Does that answer everything you had about the calcium bromide? Okay. Sorry? Okay. What do you mean 4? There's no 4. It was a 2. Okay, so X and Y. So the only information we have at this point is that calcium, when it reacts with chlorine, forms Ca1Cl2. So calcium, when reacting with an element, chlorine, in the family of the halogens, forms this formula, where calcium is 1, and the chloride, or your halogen, needs to be 2. Where's bromine? Same family as the chlorine, we would expect the same type of chemical composition. So when we go back down to this, X should be 1 for our calcium, and for the bromine, it should be 2, because it's in that same chemical family. Does that make sense? Yeah. So what we're looking at is chemical families within the periodic table to predict some trends. Okay? And we have no discussion yet about the organization on which one comes first, or why we're doing 1 and 2. All we've told you is it is 1 and 2 in one case. Can you predict from that? That's all we're asking at this point. Does that work? Now, you're covered now too? Any other questions with this? Okay. So now what we're going to do is actually start to get into a little bit of the understanding on why we're getting these different types of chemical interactions and the trends that we're seeing in the periodic table. Okay? When we're going through and building calcium chloride or calcium bromide, so let's go through and just say, let's draw it out like this. Yeah, let's just stick with that. Just one bromine for the moment. If we're going to bring a calcium atom near a bromine atom, okay, eventually they'll form a bond. What's going to be the thing that's most likely to contribute to that bond? Why the electrons? They're on the outside of those structures. If we take two spheres of our atoms and we bring them near each other, the first thing that's going to interact between those two is whatever's on the outside of that structure. So the most likely thing to be contributing to making the bond between calcium and bromine is going to be whatever exists on the outside of each of those atoms, which is the electrons. We'll get to valence in a second too. Okay? So what we now need to come up with is a way to explain where the electrons exist, because at this point we've only got protons and neutrons in a nucleus, and then we just said we have a sea of electrons around it. Okay, we actually didn't even say sea, we just kind of said, let's just leave that alone for a moment. Okay, so now what we need to do is come up with an understanding of what's happening with the electrons. Where do they exist, how do they move, and how can we generate these bonds? Okay. As relatively simple as a question as that may sound, did that sound simple, first off, as a question? Where the electrons exist? Okay, it's not too bad. The explanation of that comes back to something known as Schrodinger's wave equation, okay, which I was really hoping I could find the equation, nice and simply put, to put up on the slides, because it's a disaster to look at. Okay? It typically requires some pretty hardcore mathematics to go through and explain. And it's usually enough to make everybody panic, even seasoned chemists. Okay? But it's actually kind of neat to actually watch someone play with. What it's coming back to is this wave nature behind, ultimately, electrons as well. Okay? So what we want to do is, before we get into an electrons being both a particle and a wave, we want to explain something that is a wave already. So when we look at light, light is already in the form of a wave. Sound is in a wave. Okay, how do we know that? Well, if I shout at the wall over here, you all can hear me back there. Why? Okay, it can bounce and spread throughout the room. It will fill the room. Same thing happens with light. The lights up here are emitting light, And where's that light going? Everywhere. It diffuses out. That's the property of a wave. When you throw a rock into a pond, what happens to the wave? It spreads out evenly, relatively evenly. Okay? So what we're looking at is this wave property and how that explains some interesting physical features. So before we get too much into it, we want to look at the different properties of a wave. So we've got two possible waves shown here. And we want to come up with ways to describe these two waves. So what's the difference between them? Okay. Could look at the frequency of it. What do you mean by frequency? Okay. Within a given span, how many oscillations do you get? Okay. So when we look at our top one, our red line, we have a low frequency. Because if we compare a standard set, let's go here, we see different oscillations happening in each of these cases. So your frequency is just to measure how many oscillations happen within that given span. In our low frequency, we only made one repeat. In our high frequency, what happened? 1, 2, 3. Okay, we pulled off 3 repeats. So what we're looking at is an increased frequency within that. So we could look at the frequency. What else could we look at? We can look at the wavelength. What's happening with the wavelength? I know it's kind of small to see. We're looking at the distance between those peaks. Okay, that distance is referred to as wavelength. I might regret doing this, but I don't think the textbook goes into it, so it's not too big of a deal. The symbol we typically use for wavelength is lambda. For frequency, our frequency symbol is, I believe, nu, not to be confused with V. Okay, they're different things. What does V stand for? Velocity. Lowercase v is your velocity. We aren't using V in this case. It's nu representing the frequency. Okay? These two species can be combined with our understanding of the speed of light. Okay, so our definition for our speed of light is going to be 3 times 10 to the 8th meters per second. Okay? So we now have some understanding of what puts together these individual waves. Okay? Based on what I saw in the textbook, you don't have to do any mathematics with this. So hooray. Sucks for you if you have to move into 151. Okay? You'll have to do a lot more. You'll actually have to do some mathematics with this. Okay? So the next part is to look at all the possible light energies. So light is a form of the electromagnetic spectrum. So it's just a small section of energy. So what they try to do with this figure is represent what we see. So our eyes respond to that particular energy, and we translate that energy into color. That's what our brain goes through and does. It turns out there's other energies. So what ends up happening is we can change, okay, the wavelength or the frequency of that individual light pattern. If we do that, that can start to change what we see, ranging from blue up to red. Or, if we continue to change it, it now moves outside of the realm of what we can see, and we move into different energy spectrums. That's where infrared energy comes from, microwaves, TV, radio. Okay? Cosmic rays, gamma rays, X-rays, ultraviolet. Okay? All of those are individual sections of that energy spectrum. Why do we give them different names? What's that? Comes back to a different form of the electromagnetic radiation. Can we see X-rays? No. So why do we call it X-rays versus visible light? Because we can't see it. How we interact with that light is different. So if we take a look at ultraviolet versus X-rays, do we interact with that light or that energy differently? Well, we can't see it, so in both cases, well, if we can't see it, then it must be the same. Well, it turns out X-rays do something different than ultraviolet. Okay? They excite atoms or molecules in a different fashion, which means we'll give them a different name. So each of these energy forms has a slightly different chemical property, or effectively chemical property. They respond with different molecules differently, and because of that, we give them a different name. Okay? I would say probably the more important thing off of this is to look at energy. We didn't talk about energy with these yet, but a nice thing that can be helpful is if you take a look at the energy line here. Okay? For an individual light, we can generate energy. Does it make sense to get energy from light? Yeah, how do we know that's true? Solar power. How did we get the lights in this room? We put in electrical energy, which caused a chemical fluorescence. Okay? So light is a form of energy. So we could look at the wavelength and the frequency, or we could try and respond to these things according to energy. So let's go back to what we can visually see. Which is higher energy, red light or blue light? Okay. The way I like to think about it, what's on the opposite end of, what's the closest next energy level for our red? After we push beyond 700 nanometers, we get into what? Infrared. Okay. When we push beyond blue or purple, what do we move into? Ultraviolet. Between those two, when we walk outside, right, we have this fear, particularly in Arizona, that we need to protect ourselves from that excessive energy coming from that sun. What's that excessive energy that we're protecting ourselves from? Ultraviolet, UV radiation. Which is higher energy, purple or red? Purple. Okay. We're afraid of the ultraviolet light because it has a high enough energy to do damage to our skin. The red light, or infrared, doesn't have that energy to be able to cause that immediate damage that we get from the ultraviolet light. Okay, it does different things. Don't get me wrong there, it does different things. But the time scale on that is skewed. Okay. Infrared is a form of heat. Okay. Most people, when they start to get really, really hot, don't stand in the really, really hot. Okay. Whereas ultraviolet, we don't get that heat response. So we don't have a way to naturally avoid that energy. So that's why we use SPF for different suntan lotions or sunblock lotions to protect ourselves from that energy. Okay? Question?
I was going to ask what's in them. I've been told, like, sunblocks really do block the bad UV rays, like there's UVA and UVB, and it blocks the bad ones, but I don't remember.
Ultraviolet light, what it does is excite electrons. That's exactly what it does. So within an individual cell, if you excite electrons, that electron now has higher energy, and it can go off and do damage. Okay? What your sunblock does is it is excited by the light instead of your skin. Okay? So those individual molecules absorb that light energy. Double bonds. Yeah. Carbon-carbon double bonds, that's about it.
Is that just oil attracting it?
Probably just oil focusing the light onto your skin. Was there another? I think there was another question. Okay, I thought I saw another question. Okay. Any other questions about light? Okay. What happens with this prism? When we see this visible range, if we take a prism, okay, has anybody used prisms before? Okay. You've probably seen prisms before. Anybody seen a rainbow? Whoa, double rainbow. What's happening to get that rainbow? White light is passing through a prism. What's the prism? Raindrops. Okay? So when it hits the raindrop perfectly, the raindrop will act as a prism and generate that rainbow effect. So when we shine light, we can see a complete spectrum. Okay? A continuous spectrum of all of those individual colors. Okay, so when you look at a rainbow, it completely transfers smoothly across. It's not blue, or sorry, purple, then blue. What's next? Then green, then orange, yellow, or red. Okay? You see a spectrum, it shifts gently between those.
Okay, so I have heard about UVA and UVB. What are they though? I don't remember.
They're different energy forms of
Are they,
ultraviolet
like,
light.
on different parts of that?
They're in different sections of the ultraviolet light
But
spectrum.
there's more than just A and B.
A and B is just categorizing different energy levels. That's all it is. Okay? Yeah.
How would you ask this right on the test?
Exactly.
I could ask different energies. Which is higher energy, which is lower energy?
So should we memorize this spectrum?
You should memorize the colors and their sequence within them, which you may have already seen. I didn't do a very good job of. How can you remember all those colors? Okay, a common way to do it. After a famous person within our classroom, Mr. Roy G. Biv, standing for Roy being red, orange, yellow, green, blue, indigo, violet. Okay? That gives you all of the colors. You then would have to go through and put in the energies. Which one's the higher energy? Violet is our higher energy, so you could write down your Roy G. Biv and then go through and mark this as high energy and low energy. Because we haven't looked at a formula for the relationship between frequency and wavelength, I won't throw those questions at you. I might throw wavelength at you. Okay? What's the difference in our wavelength?
Unless it gets higher, it gets longer. I mean,
True. Which color has the higher wavelength? Okay. So now you'd have to go to your chart and have that memorized. I know I've got it written backwards. Violet happens to be what wavelength? 400 nanometers. Red happens to be 700. So which one has the longer wavelength? Red. That's the bigger number. Okay. So you could write out high energy on those, and then we could go through and specify longer wavelength. Whoops. Sorry.
So then just memorize this frequency decreases, wavelength increases.
Don't worry about the frequency one. What was I doing? Shorter. Shorter with our violet and longer wavelength with our red. Okay. Like I said, don't worry about the frequency because I personally think that's not a particularly easy concept to keep in your head beyond having it strictly memorized, and I prefer you to not memorize as much as possible. Okay? Yes?
Would you ever ask, like, what comes after, like, the microwave? Like, would you give us, like, space?
That is a valid question. I don't think I will ask that. I'll leave that for future classes. Okay, we'll focus in on just the color spectrum, your visible light. Okay? So our visible light gives us a continuous spectrum of light. We don't see individual breaks within it. Okay? So one of the assumptions that we could go through and do is that, or one possible explanation, is that we could go through and then say, well, all things that we see give us a continuous spectrum of light. Okay, well, does it make sense for that to be the case? Okay, if we see red, when we look at the prism, should we see blue and green and yellow in there as well? No, why not? Because if we saw all those colors, we wouldn't see red, we'd see white. Okay, so how can we see different colors? Well, that inherently means that some colors are not shown. Okay, which is kind of an odd concept to deal with. Bohr, which his name hasn't shown up quite yet, but he shows up on the next slide, went through and took some particular gases. They've already done this with your noble gas, or sorry, your noble gases. You get your neon lamps, argon lamps to get those different colors. And what he went through and did and said, okay, why are they different colors? I want to see what makes up the colors of that. Okay? Because what's happening when we get those colors? We're putting an electric current into that element, and that element is not somehow now spitting out these colors. Where are those colors coming from? And that's what he was trying to predict. Something has to be changing within that element to give it, okay, to give those colors.
Are you talking about the colors you would see if you were looking at a prism? Or like the
In a prism. Well, it's actually going to be both. Okay?
So, like, how do we perceive color then? Is it just based off?
What we perceive is the individual, our eyes have different responses to different wavelength lights. Okay? So when our eye sees red, red energy light comes in, hits our eye, it changes the structure.
So
Our brain then goes, oh, structure changed, that's red.
So this might sound stupid, but like our clothes, like, are you saying that they have like energy?
It's the light reflecting off of them. Okay? When we see a purple shirt, okay, what light is it reflecting? Okay? If it absorbed that light, we can't see it because it's been absorbed. It's been removed from our vision. So if we see a purple shirt, the light that it's reflecting would be your purple light. It's not absorbing that particular light. So when we see an individual response, we get an external light source comes down, hits our individual clothes. Whatever light is absorbed is not reflected. We then see that reflected light and translate that into a color. Yeah, you get a couple different tiers pushing through that. Okay? When we go through and take a look at individual samples, say with these element lamps, okay? He took a look at it and said, let's put it through a prism and see what it looks like. Let's see what individual colors are contributing to make that, that overall color that we're seeing. And when he went through and did it for certain elements, instead of seeing a continuous spectrum, okay, where you might see one darker than the other, he saw distinct lines. So in this case, this was, what does it say? Which one is this? Because I don't know the line spectrum. Hydrogen. Okay. When he put in hydrogen gas and then pumped a bunch of electric current through it, and then looked at the light that was emitted out of that, you didn't see a continuous spectrum. You saw 3 bands. One purple, one this kind of blue-green, and one red. Well, that's kind of odd. Why not see the continuous spectrum? So that's where Bohr had to think about what different things were in an individual atom to explain that. And what he ended up deciding is that the electrons are not now spread all over the whole place. Because if they're spread all over the place, when they change their energy, you're going to see a continuous spectrum of that. Okay? They have to be in defined relative locations. So that when we go through and pump electric current into it, we can now excite those electrons to a different energy. When they relax back down, they relax in very particular patterns. And that's how we see the individual lines of the emission spectrum. Okay? Not an easy concept to get through, okay? But that's ultimately what's happening with this. So that's his experiment, and we'll look at the conclusions of that in a second. There was a hand.
So you're saying the hydrogen does not absorb red, blue, green, or white? That's why.
So yeah, color is a difficult concept to deal with. What we're looking at is different processes. In this case, what's happening is a direct emission of light from this sample. When we're looking at what we visually see, it's not an emission. Our clothes are not emitting purple light or pink light, okay, because they aren't being electronically excited. What we're seeing is the lack of absorption from our white light source. Okay? Color and vision are very difficult concepts. You've got to be careful with approaching those. And I'll kind of leave that for biology or a future class to discuss it because we don't need to get into too much detail on it. Ultimately, what's happening with this experiment is we are exciting a sample, causing it to emit light. In the process of that emission, we can pick up these particular energy levels. Yes?
Change that happen from, is that green to red?
Don't look at that necessarily yet. But
Because electrons, right? It's
yes.
because of this, like, the
So
wave.
each of those colors is due to an electron moving from very particular locations within the atom. Okay.
It has nothing to do with the, the wave, like it jumps really high because of the electron.
It doesn't directly have anything to do with that. As the simple answer, it doesn't. As the much more complex answer, it absolutely does, but you really don't want to get into that. Trust me. Okay? So what Bohr went through and did with these individual light spectrums is he said we had to have something known as orbitals. Okay? And these orbitals were at different energies. So that what happened is I can now move an electron from one position to another. Okay? If I have a happy little hydrogen, okay, we go back to our color spectrum here. If I start with just a happy hydrogen, we don't see any color. Hydrogen's around us all the time. It's colorless. But if I go through and now pump a bunch of energy into that hydrogen atom, it freaks out. And the one electron it has, now instead of being at a nice low energy, jumps up to a higher energy. Okay? By pumping that energy into it. Okay? At a higher energy, what happens? Okay, it's moving faster, starts to panic. It's also unstable. Okay? So consider if all of a sudden you were walking down the street and all of a sudden you were picked up and thrown 100 feet in the air. Okay, what are you going to do? Other than probably pee yourself. Okay? Your first response, ultimately once you get up into the higher energy state or tossed up in the air, is to do what? Get back to a lower energy state. You don't want to be thrown up way up in the air. Okay? So the electron does the same thing. That energy has to go somewhere, though. In the case of us being tossed in the air, that's going to result in a not very nice impact when we hit the ground. With our electrons, that energy has to go somewhere else, and the electrons can't absorb that energy. Okay? Our bodies can absorb it when we hit the ground. Not nicely. Okay? The electron can't. So what does it do with that extra energy? Electron. What does it do with that extra energy? It has to convert it into something else. What is it converted into? Light. So what we're visualizing is we've scared the crap out of an electron, and then it calms back down. And in that calming back down process, it's now spit out or released that energy. That energy is generating this light. Okay? So to do that, we have to be able to jump between particular energy levels. To get individual bands of color as opposed to a continuous spectrum, we have to have very particular energy levels to jump back and forth between. We can't just take that electron and move it to any individual position. It has to go to a particular step before it's allowed to jump back down. And what we're looking at in that case is what's known as a discrete spectrum or discrete energies. I'm loving how well that color shows up. So if we take a look at our nucleus, okay, in the dead center, you can see that spot. Okay, and I'll attempt to kind of dot in what we're showing on the outside. We've got a bunch of spectrum or lines on the outside. These are supposed to represent the different energy levels for where the electron can exist. And when we look at hydrogen, okay, and this is true for all chemistry, we always strive for neutrality, the most stable position. That single electron is going to get as close as possible to the nucleus without impacting it, because then it gets destroyed. Okay, so our electron is going to want to exist right up next to it. Okay, lowest energy, because we're now stabilizing the negative and positive charges with each other. When we pump a bunch of electric energy into it, that electron gets launched up to a higher energy state. Okay, so this would be our lamp. Okay, that electron can now move, and I'm going to say it moves around just on the outside just to get it to a different position. Eventually it says, this is crazy, I don't want to be up here, and it goes back down to its lower energy state. But remember, we can't create or destroy energy. So when it comes back down and it loses energy, that energy has to go somewhere. That energy is released in the form of light. Okay? In the case of our atomic line spectrums, we see it as light. Okay? So what Bohr ultimately said was that we had to have these individual steps. Because if we didn't have individual steps, we would see a continuous light spectrum. We don't see the line spectrum that we pick up with these. Okay? So what does that mean, or another way we could look at it? Okay, this is ultimately an example of your quantum concept. A continuous spectrum would be like putting a ball. Okay, so we could start with our ball at the lowest energy, the bottom of all of those steps. If it's a continuous energy, I can move that ball up to any point and let go, and it immediately falls back down. Okay? It runs smoothly between all those different energy states, or different heights. Okay? Very, very smooth and continuous. But in the case of the quantum concept, what we're looking at is a staircase. So I can take that electron and I can move it up to any one of those steps. When I let go of it, that ball now has the ability to bounce down to the individual other steps. Okay? That individual bouncing is effectively what's happening with our discrete energy levels. Okay? Our tennis ball can only really be at any one of those individual steps. It can't be at any energy level in between. Okay? I know it's not an easy concept. So questions?
So when we set all the electrons go to a different level.
The one electron that's at that excited state, the highest energy one, just that one. Okay? So when we look at the light spectrum and we're seeing different colored lights, what's happening is that that electron is jumping from different energy states. Because remember, the energy must be emitted. Is all light the same energy? No. Remember, we said blue light was higher energy than red light. So the bigger the jump, okay, from the excited state to the ground state, the bluer it gets. Okay? Yeah.
And this is happening to like all the electrons at the same time?
This is happening to an excited electron, a single excited electron.
So it's possible to just like have one and the other one's just gonna stay where they are?
Yep. Okay. Why do we see multiple colors if it only happens to one electron? In an individual sample, how many molecules or atoms of that element are we going to have? If I asked you to grab a single element right now, how many of you could grab one element? You're not going to be able to do it. Okay? Go back 100 years, you're not going to be able to do it even worse than you can not be able to do it now. Okay? So what they did is in those lamps, they aren't exciting a single atom. They're exciting the entire sample, which means within all of those single atoms, electrons are being excited to different discrete energies. Whichever ones are valid jumps generate this color, okay, or the line spectrum that we see. Okay? Questions about that? So, what's the big lesson to come out of all of this? Electrons exist in orbitals. They are not a sea of electrons. They are in very defined, particularly energy levels. And as we go through our periodic table, we're going to end up putting electrons in different energy states. Okay? As we move to, say, hydrogen versus, because I'm already in that example, francium, we're adding more electrons in. The electron, the last electron added to francium, should it be at a higher energy or a lower energy than hydrogen? It's an interesting question. Okay. Last electron added to hydrogen versus francium. Okay. The electron in francium, that last one, should it be at a higher energy or lower energy than the hydrogen? Higher energy, it's getting further away from the nucleus. Hence our size gets bigger. So when we look down that column, that last electron is added at the very, very end, which means it doesn't see the positive charge as well as in, say, the hydrogen. So when we put that single electron into the hydrogen, it's now very close to the nucleus. Its charge is effectively balanced, whereas that really far one isn't balanced as well. So it is a higher energy state. There was a question over here before we got into that.
Kind of hair dryer. When
Let's
you
see.
make the models of the, okay, I remember making them in biology, and they always, if it had like 4, it was always like 2 and 2, or 1, 2, 3, 4, on the outer valence, or whatever it's called. Does it matter where you put the electrons on the outer?
I think what you're talking about is when we get into bonding, we aren't quite there yet.
Oh,
Okay. We'll see what happens as we push a little bit further.
So you said that the electron that is added on hydrogen and francium on hydrogen would be with higher energy.
Lower energy.
Or lower.
Because
the
it's-
distance between the nucleus and the electron is smaller.
Which means that those charges are neutralized.
Okay.
Whereas in francium, that electron is much further away. We can't neutralize that charge as well.
So, all the electrons need the same energy, so not really, let's say.
The first electron put into any element is always going into the same energy. Okay, so now what we're going to start to do is think about how we can put our different elements or our electrons in. And that's going to be the next question. What energy levels can we deal with? So this is our evidence for our energy levels. The different colors of light within our line spectrum, which means we're seeing electrons jump from different discrete energy levels. Without that discrete energy level, we don't see a single line. We would see a continuous spectrum. Remember, it's the ball rolling down. We'd see all of the light pass through. Okay? So what does that mean? Oh, come on, where's my picture? Okay, so we could look at atomic fingerprints. Each element's going to have its own distinct atomic fingerprint. Because as you add more electrons in, those electrons start to affect each other and their individual energies, so you'll see different emission patterns. So depending on what element you're working with, you'll see different line spectrum. So they gave you a couple distinct ones here. And because each of them has a different number of protons and electrons, each of those electrons goes into a slightly different energy, which means we see a slightly different line spectrum. Yes?
Considering how narrow the visible band is, it's kind of amazing that they all.
It's ridiculous.
have a visible band.
Well, they do have transitions outside of that. We just can't see them. But yeah, to be able to even see this is pretty cool. Yeah. Hi. Neon lights, they're colorful, they're pretty. There are your colors. So if you combine their spectrum together, you get that individual color coming out of it. Are you changing your mind?
I didn't see what it said on the slide.
Atomic fingerprint. Okay, for each molecule or each atom, they'll have their own atomic fingerprint. They'll have a different line spectrum associated with it. Okay, would I expect you to know that? Can you imagine flipping open to a test and see, say, blue, green, green, yellow, red? What element is it? I'm not going to ask that question. Okay? The idea behind this is to show the evidence or the proof that we have distinct energy levels for our electrons. That's our conclusion. Yes?
Does gas have more atomic fingerprints than like a metallic thing?
I think I see what you're saying, and not necessarily. Okay. Gases are easier to excite. That's about it. So neon lights generate different colors. That's why for each element we see different colors from those. Okay? So now we can go to ultimately our conclusion, our electron homes. So what we've got here, we're looking at energy levels on the left, and I've got it ranked as far as highest to lowest. Okay, so energy would be on our y-axis, increasing energy. That top line is supposed to represent the energy of an electron that's not attached to an atom. Why would that be higher energy?
Because it's free.
Because it's free. There's nothing to neutralize it. So a huge conclusion to make with everything chemistry, everything that we do in chemistry strives for neutrality and lower energy. If we take an electron and don't put it near anything else, what's its charge? Negative. If we take that same electron and put it near something positive, the positive and the negative start to cancel out, which means what happens to the charge? It starts to become more neutral, which means the energy should decrease. So what we're looking at that lowest energy level is where we would put our first series of electrons. Okay? So then the question becomes is how many electrons can we put in? We aren't even quite at that. Okay? So let's put in some electrons and we decide, okay, that orbital is now filled with electrons. We have to have some other place to put the electrons now. Okay? Why do we have to go to different orbitals? What happens when I bring two electrons near each other? They repel because they're both negative. Okay? So we need another orbital or another energy level. Should that energy level be higher or lower? Higher, because we always want to go to the lowest first. So we can go through and put in a sequence of other energies. Ignore the coloring that's just supposed to show different energy levels, not necessarily the color of the visible light. Okay? So what we're looking at now is that as we build atoms upwards and start putting more electrons in, we start putting the electrons in closer and closer till almost effectively they're no longer attached. So what did that mean about the energy, which we already discussed with francium versus hydrogen? The last electron in francium is a much higher energy. Why is it much higher? Further away from the nucleus, less stable. If we were going to look at our energy levels, it should start to approach that completely free line. Should it ever exceed that? Why should it not exceed that energy level? Because then it's not part of the atom. Okay? So when we go through and look at this, these energy jumps, the first jump is pretty big because we're now getting a substantial distance away from the nucleus. Okay? After that, we can only go to a certain threshold. That threshold is when we've now completely removed it from the atom. Okay? So we see these distinct energy levels. And what Bohr was able to do is he said, okay, if I start with, say, something like hydrogen and I take an electron, I excite the crap out of it, it jumps up, it gets excited and falls back down, that releases the light. Okay? That's what happened with those line spectrum. We took the electron in its ground happy state, we put in a bunch of energy, scared the crap out of it, jumped to a higher energy, moved around up there until it finally said, heck with this, returned back to its ground state. That loss of energy results in our light spectrum. And that jump is where we see our colors.
Is it always light that it produces?
It's not, well, it is always light. Is it always visible light? No. Okay. So it will always be some form of the electromagnetic spectrum, okay, which we could call that whole thing being light. Okay, but it's not necessarily going to be just the visible light. So we happen to get lucky because we could see those individual jumps, okay, which is what Thor was talking about earlier. It's pretty amazing that we could actually see these distinct energy levels by looking at that color, that our eyes happen to respond to that exact same thing.
So when it's jumping and falling and putting out that light, is it putting out light the whole way it's going up and the whole way it's going down?
Going up, what's happening? It's gaining energy. We have to supply that. There's no emission there. We don't see any light. If anything, we'd see a lack of light. Okay? Only when it falls back down do we see that light. Once it does, so that's what happens with our steps. We must jump from 1 to 2. So in that jump, it's not a gradual step, it's boom.
That's what those colors were. Was that
Is that individual jump. What happens if instead of jumping from green to black, we did green to blue? Less energy, different color light.
When an electron is excited and it jumps to a different level, it always has to jump back down? Or is it possible that
It always has to jump back down. How it jumps back down is different in different cases.
So it jumps down when you give it energy. What if you want to bring it down?
When we put our electrons in, we always put them at the lowest energy. Could it possibly jump lower?
It's never down. It's the other way.
It never starts at the highest state. Because remember, everything strives for neutrality, lowest energy. Okay? Perfectly easy to understand, right? There's no possible way we could make that more complicated.
No.
Yay, complications. Turns out that as we move up in these energy levels, we get those energy levels splitting into different possible orbitals. So as we move up from black to blue, our black energy level has only one possible energy state. When we jump to our blue, our second energy level, there are two possible states. So we add one. What happens when we jump to green? 3 possible energy states. When we jump to yellow, 4 possible energy states. Orange, 5 possible energy states. Okay? So these extra possibilities are how we end up filling our periodic table. Okay? That couldn't possibly get any more complicated either, right? Wrong. Now we can look at something known as an orbital orientation. So we start with an energy level, then we move into orbital types. Okay? It turns out our different orbital types can then be arranged in space, okay, differently. That arrangement in space generates a new energy level. Okay? Can that possibly get more complex?
Yes.
Yeah. Next, last piece that goes into that is what's known as the electron spin. Okay? And we'll look at each of these sort of. We won't get into the electron spin so much. Each orbital can hold 2 electrons. Okay? So that's kind of interesting. How do we get 2 electrons into one orbital? The negative should repel, right? How could they possibly be in one orbital? This last thing is kind of a confusing concept, electron spin. What we're looking at is effectively a sphere. An electron of a negative charge can spin clockwise or counterclockwise. That pairing allows us to put 2 electrons into an individual orbital. Okay? Kind of neat. Like I said, we won't get into that one too much. You just have to realize that you're looking at 2 electrons per orbital. Okay? So what does all this mean? So what we just went through and did is looked at specifying where our energy or where our electrons live by individual classifications. Okay? These classifications can be known as quantum numbers. We aren't going to address them as numbers. You're just going to be responsible for the different pieces that go into it. So it's difficult sometimes for students to realize what these different things mean. Okay? Well, let's change electrons to you. Where do you live? Okay? Everybody's happy. Oh, I live in my house. Okay? Where does an electron live? Lives in its house too. How do you get to your house? What do you need? You need an address. You need a street. You need the city. You need the state. That information is just like our electron homes. The state is kind of the bulk general classification on where you can find it. There's your energy level. We can zoom in a little bit closer and say what city within that state? What orbital type are you looking at within that energy level? Okay? What street? What orientation? What's the actual address? That's the electron spin. Okay? So orbitals are easier than humans because on an individual street, as far as electrons are concerned, you can only put 2 electrons. Whereas on an individual street with us, we could put an infinite amount if we really wanted to. Okay? Because we can make the street just go around in circles, right? Okay? Just kind of want to mention this. You feel free to pack up. We will start here on Tuesday. We end up with the 3 main types. So when we went through and looked at our black orbital, this is what its type is, that one type. Okay? When we looked at the black one, we said there was only one possible orientation. Take a sphere. What happens when I turn the sphere? Does it still look like a sphere?
Yes.
Looks exactly the same. When we moved up to the blue, we get 2 types. We get the first one that we started with and a new one. When we take a look at this, if I rotate this, is it going to look slightly different? Yeah. There ends up being 3 possible orientations with the dumbbell shape. One along the X, one along the Z, one along the Y. 3 possible orientations, 3 possible that type orbital. The very last one is what's known as your D. I guess I can write those in here. That one, again, you increase the possible types of orientations. Okay? Strictly with the shapes, you're responsible for knowing what these are. Sphere, dumbbell, how about cloverleaf? Okay? Beyond that, I don't expect you to do much else with knowing these different orbitals. Okay? So like I said, we'll pick up there. Thanks for your patience.